I'm Dr. Jinish. In this session, we will be studying about rate constants for zero, first and second order reactions. At the end of this lecture, students will be able to derive equations for rate constants for reactions, derive equations for half-life for those reactions, and discuss Arrhenius theory and effect of temperature on rate constant. We will start with zero order reaction. In zero order reaction, rate of reaction is independent of concentration of reactants. So if you increase the concentration of the reactant or decrease the concentration of the reactant, rate of reaction is not going to change in zero order reaction. We consider a zero order reaction. A gives products. Here A is the reactant and this reaction follows zero order reaction. We will be able to write equation for rate of reaction minus d of concentration of A with respect to time. As per the integrated rate law, we will be able to write another equation, rate of reaction equal to rate constant into concentration of A raised to n. Here order of the reaction is n equal to 0. So I will be able to rewrite the reaction equation as rate of reaction equal to K into concentration of A raised to 0, and we know that any number raised to 0 is 1, so the equation becomes rate of reaction equal to K. So this equation I write it as equation number 1 and this equation I write it as 2. In both the cases, left hand sides of the equations are same, so I will be able to equate the right hand side. So if I write the equation by equating the right hand sides of the equation number 1 and equation number 2, I will get equation like this, minus dA by dt equal to K. K is rate constant. Now, before deriving equation for the rate constant, I have to rearrange this equation in this way. Minus d of A, I will keep it here, and dt I will take it on the right side. Again, I am changing the sign of the equation, then equation will become minus k dt. Now, I have to integrate this equation. I will write it as equation number 3. So, integrating equation number 3, what we will get? Integrating A from initial concentration, that is A0, to the final concentration, I will write it as AT, equal to rate constant is a constant. I will integrate the time from starting the experiment at that time t equal to 0 to the experiment at time t. So once we integrate this equation, we will get an equation like this. Concentration of A at time t minus initial concentration equal to minus k into t. If you rearrange this equation and if you are trying to get an equation for the rate constant, the equation will be k equal to A0 minus AT divided by t. So by rearranging this equation, we will be able to get rate constant equation for zero order reaction, and we will write this equation as equation number 4. So this is the equation for rate constant for first order reaction. If you want to get the unit for this rate constant, and we know that what will be the unit of the rate constant by using that equation, mole raised to 1 minus n, liter raised to n minus 1 per second. If you substitute 0 for n, then you will get an equation, then you will get the unit as moles per liter per second. So this will be the unit for this first order rate constant. Now if you want to get half-life for this zero order reaction, we can rewrite this equation in terms of T. Then we will get an equation like this: T equal to initial concentration minus final concentration divided by the rate constant K. Now at half-life we will be representing as T half. At half-life, concentration will become half of the initial concentration. So substituting the values in this equation, you will get an equation for half-life: T half equal to A0 minus AT, we can write it as A0 by 2 divided by so we can write like this: 2 of A0 minus A0 divided by 2 divided by K. 2A0 minus A0, A0 by 2K. So I can write the equation for half-life as T half equal to initial concentration of A divided by 2 into rate constant of that zero order reaction. So zero order reaction half-life equation is initial concentration divided by 2 into rate constant. Similarly, we can derive equation for the rate constant for the first order reaction. So for the first order reaction, I'm taking an example. Reactant A is converting into a product. Rate of the reaction can be expressed as minus d of A by dt. As per the integrated rate law, we can write equation for rate of reaction equal to K into concentration of A raised to n. Here is a first order reaction, so A raised to 1. So I can write reaction K of A. Equation number 1 and this one equation number 2. I can equate both equation number 1 and 2 because left hand sides of both equations are same. So I can equate the right hand sides of these two equations. So I will get an equation minus dA by dt equal to K into concentration of A. I am rearranging this equation. D of A divided by A equal to minus K into dt. Equation number 3. Next, we have to integrate this equation number 3. Integrating equation number 3. Zero order reaction equation we have already derived. So equation was AT minus A0 equal to minus KT. So I'm writing that equation. I'm rearranging this equation as this equation resembles with y equal to mx plus c. This is an equation for a straight line. So if I draw a graph with t in x-axis and concentration with respect to t in y-axis, I will get a straight line for a zero order reaction. And if you calculate the slope will be giving you information about the rate constant. Similarly, we can derive rate constant equation for first order reaction. We will consider a reaction where reactant A is converted into products. We can write the equation for rate of a reaction. Minus dA by dt. As per the integrated rate law, we can write equation for rate of a reaction. K into concentration of A raised to N. N is order of the reaction. Here A is 1. So you can write as K of K into concentration of A. Equation number 2 and this is equation number 1. We can equate both these equations, equation 1 and 2. Left hand sides are same. Right hand sides we can equate. So if we equate right hand side, equation will become minus dA by dt equal to K of concentration of A. I will rearrange this equation. Let the terms related to concentration of A on one side and terms related to time on right side. So the new equation will be d of A by A equal to minus K into dt. So integrating equation number 3, we will get ln of AT minus ln of A0 equal to minus KT. So if I am rearranging this equation for K, then equation will become ln A0 minus ln of AT divided by T. So this is the equation for rate constant for first order reaction. For first order reaction. Now if I need an equation for half-life, so I can rearrange this equation for T. I can write ln A0 minus ln AT by K. So at half-life, T will become T half. Concentration of A will become concentration of initial concentration divided by 2. So by rearranging this equation, substituting all these values in the previous equation, T half equal to ln A0 minus ln A0 by 2 divided by K. So this equation, if I rewrite, ln A0 divided by A0 by 2 by K, because we know that ln A minus ln B is so we rearrange this equation, we will get ln 2 by K. Ln 2 value, we know that it is 0.693 divided by K. So if you see this equation for half-life of first order reaction, the equation is 0.693 by K, and we can say that half-life is independent of initial concentration, because for the half-life in this equation there is no terms related to concentration of the reactant. So we can say for half-life determination for first order reaction, we require only the rate constant for doing the calculation. First order equation we can write like this: log of AT minus ln A0 equal to minus KT. I am rearranging this equation. Ln of AT equal to minus KT plus ln A0. If you see A0, we know that there is a constant for this reaction. So we can write this equation as y equal to mx plus c. In this form, this is an equation for straight line. So what does it mean? If I am plotting a graph x against y, here x is t and y is ln AT, I will get a straight line which is having a negative slope. Why we have a negative slope? Because of this negative sign. And if you take the slope of this graph, will give you information about the rate constant. Imagine that you have data of a reaction where concentration at different times are given, and you wanted to check whether that reaction follows first order or not. What you have to do, you have to plot a graph against time and ln of that concentration of those reactants at different time, and check are you getting a straight line or not. If you are not getting a straight line, means that reaction is not following first order reaction. If you are getting a straight line, that means that reaction. Hi students, hope all of you are fine, and also hope that your studies are also going well. In this video, mainly 4 points will be discussed. First one, derive an equation for the rate constant of a second order reaction. Second one, derive an equation for half-life of a second order reaction. Third, study the effect of temperature on the rate of a reaction. The fourth one, understand the Arrhenius equation related to chemical kinetics. Second order reaction. In the last class at RUAS, we studied zero order and first order reactions in chemical kinetics, and also we derived equations for rate of the reaction as well as half-life of these two types of reactions. Now all of you know the terms and symbols normally we will use to study chemical kinetics, such as rate constant K, initial concentration of reactant A0, concentration at time t as AT, and half-life T half. Two cases of second order reactions are possible. Case 1, only one reactant in the reaction, that is A gives products. Case 2, two different reactants are in the reaction, that means A plus B gives products. First, we will consider only the case 1, that is A gives products, only one reactant. As per the differential rate law, rate of a reaction we can write it as minus d of A by dt. As per integrated rate law, we can also define rate of reaction as rate of reaction equal to K into concentration of A raised to 2. That 2 stands for second order. Now, left hand side of these both equation number 1 and 2, they are same. So we can equate the right hand side of the equations. So we can write minus dA by dt equal to K into concentration of A to the power 2. Now rearrange the equation. So you will get that equation as d of A by A square equal to minus K into dt. Now we have to integrate the above equation. So integrating from A0 to AT of 1 by A square dA equal to minus K into integrating from 0 to T of dt. We know that if you are integrating 1 by x square dx, we will get minus 1 by x plus c. So after integration, the equation becomes minus 1 by AT minus 1 by A0 equal to minus KT. Now multiply the above equation with a negative sign. So the equation becomes 1 by AT minus 1 by A0 equal to KT. Now rearrange the equation. So equation becomes 1 by AT equal to KT plus 1 by A0. This equation helps us to understand the second order reaction. Now you can write an equation for rate constant K from this equation number 5, and you can do it yourself. Now we can calculate the rate constant by graphical method also. We know that the equation for second order reaction is 1 by AT equal to KT plus 1 by A0, and this equation looks like y equal to mx plus c, which is an equation for straight line. So if we plot a graph 1 by AT against t, graph will look like this. And if you take the slope, then you will get the rate constant K. Now we can derive an equation for half-life of a second order reaction. At half-life, T half AT becomes A0 by 2. At half-life, equation number 5 can be rewritten as 1 by A0 by 2 equal to K T half plus 1 by A0. Rearrange the equation, we will get 2 by A0 equal to K T half plus 1 by A0. If you are trying to get an equation for T half, then it will become 1 by K into A0. Here you see the half-life T half is inversely proportional to the rate constant as well as the initial concentration. Now the third point is the dependence of temperature on the rate of a reaction. Chemical reactions occur due to the collision between the reactant molecules. That means the rate of a reaction is directly proportional to the collision frequency. Collision frequency is how many collisions per unit time. But all the collisions won't lead to the products. If the collided particles have enough activation energy, EA, this is the minimum energy required for the reaction to occur, then only the reaction occurs. If you increase the temperature, what happens? The kinetic energy of the reactant molecules increases. So they will move faster, they collide with each other in a faster way. So it improves or increases the collision frequency. If the collision frequency increases, then definitely the rate of the reaction will increase. So increase in temperature results increase in rate of the reaction. Now, this rate of the reaction and its effect by the temperature can be expressed using Arrhenius equation. The equation is K equal to A into e to the power minus EA by RT. EA is the activation energy, T is the temperature in Kelvin, R is the universal gas constant, A is the pre-exponential factor which is related to the collision frequency and K is rate constant. If you take logarithm of this equation, then the equation becomes ln K equal to ln A minus EA by RT. This equation also looks like y equal to mx plus c. So if you plot a graph ln K against 1 by t, you will get a straight line, and if you take the slope of that graph, then you will get EA by R. So if you substitute the value of R, which is your universal gas constant, then you will get the activation energy. Thanks for watching.